this. Do that. So we're talking today about specialized techniques, which is basically the other um, this is basically the other imaging modalities within ultrasound. So in dealing with echo, are you guys seeing this? Probably not. Hold on, let me share this. Okay, so we have the basic ultrasound. So our basic ultrasound is B mode. We have color Doppler. We have spectral Doppler, which is either going to be a continuous wave or a pulse wave Doppler of some kind. Those are sort of our basics. Beyond that, there's sort of some what can still be sort of considered basics like power Doppler and things like this. But these extra modalities, these specialized techniques, are things that have developed over the years. Again, this is a chapter here because in the previous version of Feigenbaum, they actually had a chapter specifically about specialized techniques. Now that's part of the chapter on the echocardiogram. Many of these things are just so well integrated now that they don't really consider it a specialized type thing. But for those purposes, we just want to go into a little bit more detail of these modalities. So even though Echo really started with M mode, I think you can consider M mode kind of a specialized technique of its own now, simply because B mode has taken over so strongly that in the industry, many times they don't even do M modes, they only do 2D measurements. So your question might be, why do I teach it then? I teach it for one reason, that it's on the registry. Second reason, I think it's helpful to know how they originally did measurements and stuff like that and how it correlated to 2D, because if we're measuring a wall, for example, like a septal wall in M mode, we should be able to get very close to the same measurement in 2D if our information is in fact accurate. So I think for accuracy's sake, understanding how it was done in M mode helps us better understand how to get a better 2D version of that. And so I think as a comparison, I think it's very good. In addition to that, I think that in the industry, while we've got some of these old techniques that sort of went their own way and sort of are disappearing out of the industry, sometimes they come back. It's sort of like the clothing in the 60s and 70s tends to come back. All of a sudden bell bottoms is a thing again, and big hair from the 80s and stuff like that. So stuff tends to come back in a different way sometimes. So an example of that could be using color M mode for our propagation velocities, or using color M mode to see when a valve is regurgitating rather than just the 2D information with color Doppler on. So those things can be pretty helpful. So that's kind of why we do that. So number one, it's on the registry. Number two, I want you to have that comparison as to where things came from. Number three, I personally believe that if you have really good M mode windows and you're good at doing M mode, I think you'll be better at getting good 2D windows. Sometimes we get a little bit lazy on windows because with M mode, we had to be perpendicular to the structure. You had to have good physics set up in your ultrasound image to be able to get good clarity. And sometimes we get a little bit lazy because at a lower window, it's more visible to us, but it doesn't have as good as lines per se, like those nice perpendicular lines you get from M mode. So I think from a technique standpoint, I think it teaches us better technique. I often relate it bow hunting to rifle hunting. A good rifle hunter can go be a bow hunter, but they may not be good at it. Whereas a good bow hunter is going to be a great rifle hunter because they have just different techniques that get them much closer to what they're after. So I think there's some correlation there with M mode and 2D. I think being able to have the skill to do both is going to give you a better skill set in the end. And you don't necessarily have to use it, but understanding where it came from is certainly helpful. So M mode. So what is M mode? As we know, is motion mode. And we'll just go through some series of questions, and the study guides should also be asking questions like this as well. So how does it relate to Well, let me ask you, how does M mode relate in image quality to 2D? What parameters can we measure in M mode, first of all? Can we measure velocity?
It isn't it temporal resolution?
Yes, so it is a single line of information that's drug out over time. So we on the vertical axis or the y-axis we have distance, and then the x-axis we have time. So yes, it's that information drug over time. We can see where things are moving to within the image relative from one frame to the next. What are my frame rates like in M mode? Super high, super high, super good resolution because of it, super good temporal resolution because of it. So if you're looking at a distance in a time factor, M mode is very good at that. We don't miss hardly anything. Whereas in 2D, we often get all this compounding and different image processing that occurs during that time that creates blurrier images. I was just quality controlling somebody's studies a week or two ago that I would compare them to the techs in that same facility with the same equipment. This one particular tech's images were never quite crisp. They were never quite clear. And the only difference was their motion with the transducer. They're just moving too fast as they took images, and they probably were just shooting pictures on the fly. When you're still imaging and you're trying to get good detail resolution, you need to freeze your image, scroll back, and get very fine detail. That blurry image can be enough to miss pathology. So it's important that our images have very, very good, very high frame rates, particularly in echo and even more so in fetal echo because the heart's moving so much faster. And then we've got our 2D echo, which is our B mode. We've got color B scanning. So the image on the lower right there, you can see just has a colorized grayscale. So you can use those colorized maps. How many of you have dabbled with those colorized maps? Anybody? So feel free to use them. And you know what? So the post-processing maps, literally you can freeze the image, you can change the post-processing, you can run a clip just in review mode before you accept it. And sometimes you can do it after you've accepted the image out of the database. But you can just go through the maps and change the contrast. But it's good to go off an image that looks pretty decent. And then the idea is that you're trying to see if you can give enough contrast to distinguish any differentiation between masses and tumors and thrombus and stuff like that. Just to be able to see it better with your eye. Maybe it's to see the endocardium better as you're doing your Simpsons. Freeze your image, let it or run the clip in review mode, and then go through your B mode maps, and you can see if one of those pops out to your eye better, if you can see that definition more clearly. And or you can use those B mode color scanning things too. So they're just colorized grayscale essentially. That colorized version of that just pops things out in a different appearance to your eye. And the whole concept is that we're picking out pathology, that we're seeing endocardium a lot more clearly, stuff like that. So use those after the fact is most helpful. You can change it on the fly, but if you're changing on the fly, you may not appreciate the real subtle differences that you may find otherwise. But certainly can be used. It can be used also in spectral Doppler. For example, this spectral Doppler is colorized. It's not just in black and white. It is overgained, but depends on what we're looking for. Um, the gain may not be high enough if we're looking for regurgitation. It's too high if we're looking for aortic valve flow.
Scott,
Yeah, go ahead, Kathleen.
how do we do? We've never done color M mode. Like we've never done it on the machine.
Right.
How do you do that?
So it is actually very simple, but the steps are important. First thing, most important, is turn your color Doppler on, and then turn your M mode on. If you do the M mode and then color, it may not work on a lot of systems, but if your system will do it, you simply turn color Doppler on, then you put your cursor through it and turn M mode on. The reason we don't often do it in our lab is because it's often used to visualize pathologic conditions, which we simply don't see. So for example, if we're doing if we're doing mitral valve propagation velocity, we need to, well, we could do it with propagation velocity, actually, we just haven't put that in the protocol. So you put your color Doppler on, you would have it run from the mitral valve tips to the apex. That color Doppler would have to cover that whole area. Then you just run the cursor through your, let me turn on.
What view are you talking about?
That's a good question. So in your apical view, apical 4-chamber view typically. Sorry, I'm trying to.
Yeah, because he's talking about having the color go all the way to the apex.
Yes. So I'm gonna turn my laser pointer on here. Going far. Okay, so apical 4-chamber view here. So you make sure that your cursor runs through the apex through where, so the valve tip is over here. Notice it's not centrally located, and that's often the case, is it's usually closer to the lateral wall. But you'll pass your cursor through that area with color Doppler on. You don't have to change your color baseline or anything like that, and that's when you get the M mode comes across, and you'll measure that angle of the aliasing velocity as it goes from the mitral valve tips towards the LV apex. So that's what propagation velocity was. In this case, this is a so this is actually a transesophageal image down in the bottom right. You can tell partly because of this image on the very bottom is flipped over. So this is actually aortic valve here. This aortic valve has a regurgitation. Notice that the cursor is placed just onto the LV side of it, and you can actually see the regurgitation coming through the aortic valve. So it's just another way to document the severity of that regurgitation. Nancy, go ahead.
So when you do M mode color dot M mode, do you put the M mode line through the vena contracta?
That would be ideal, because often I would assume that they're trying to measure that vena contracta, so that would be best, yes. But it's also good for timing, so I can see timing wise that I only have regurgitation here, it stops right there. We got a regular flow there, it starts again here and goes to there. So you can tell timing wise exactly how long that's regurgitating. You can even correlate it with the EKG above it or below it, depending on how it's displayed. So it gives us great timing information. I will say from a clinical standpoint, where I've personally seen it used most, and if at all, it's only really used in that propagation velocity. These ideas of using it for regurgitation, there's very few labs that actually do this, but I think it's immensely helpful. And why don't they do it? Because they have other ways to quantify how much it is. They don't. That's just another image to take, and they just may not add that to the protocol. So it's not a good thing or a bad thing, but I think it's a helpful thing if you're able to do it. And most systems should be able to do this. So that's color M mode. Again, spectral Doppler we're pretty familiar with, color flow we're pretty familiar with. So those are really the imaging techniques, normally speaking.
I have a question.
Yeah, go ahead.
So going back to that last slide there, that bottom right-hand corner image of the TEE image, it's a semi-quantification. We're not really measuring anything off that aortic valve color Doppler regurgitation.
Correct. They haven't measured on this particular one. So we can see that if you understand that this is the aortic valve on the bottom because it is TEE, that's important to understand. Otherwise, you're assuming it's mitral valve because it's down below. So left atria is on top, then it's the aortic here. So yeah, we can see it. It is a semi-quantification. You can also see in this image that this is the aortic root, basically from here to here. That's the aortic root size. So relative to the aortic root, you're looking at how size of this is. Now, when we're comparing size of that, we actually should be talking about vena contracta. If you're in fact through the vena contracta, where it is the most narrow, you can get an accurate measurement. Now, they did not measure it here. They would probably measure that in without M mode, just from a two-dimensional picture with color Doppler on at this angle. If that's also how they're measuring it, they should actually be closer to the aortic valve tips as well. So if we get too far back, we can easily overestimate the size of that jet because it quickly expands out as it goes back into the chamber. So vena contracta is truly the narrowest portion of that jet. So yeah, semi-quantification here for sure. Could they measure it and put something on if they're in an accurate position? Yes, and that would be acceptable and that would be quantitative if we measured it. All right, tissue Doppler. So we had some exposure to tissue Doppler, and again, that's just the motion of the tissue itself. It's color Doppler based. So you can see that in these images, they often put color Doppler onto the 2D image first, and then they do their pulsed wave Doppler, which is set to be able to obtain certain tissue velocities rather than flow velocity. So that's what those are. So it's a color Doppler version of it, and then on the left here you have spectral Doppler versions of it. This would also be quantitative on the spectral Doppler because these are very accurate measurements of tissue velocity, whereas the color Doppler, just like color in flow Doppler, is a mean velocity and doesn't give you accurate velocity information. It just generally will tell you if it's coming to or from the transducer at that moment. Nancy, you had a question?
How do those views on the right relate to the waveforms on the left?
They do not.
Okay, I'm like,
yeah, I mean,
yay for me.
Yeah, I just put pictures of those. They do not correlate because this is peristernal long axis. You can see this is comparing diastole and systole between these up and down ones. So these two A and B are connected, but they are not connected to the ones beside it. So this is mitral inflow, probably from a 4-chamber view. This is also probably from a 4-chamber view. This is spectral Doppler of the flow. This is spectral Doppler of the tissue. So bottom is tissue Doppler, the top one is that. So again, those came out of the book just the way they are, but yeah, I was just putting the pictures there to
Hey,
talk
Scott.
about Doppler. Yeah, Mike, go ahead.
How would the spectral Doppler differentiate between, if we're using pulse wave, like the bottom right picture, the top, we can see that the IVS is like in blue, but the posterior wall is in red, but they're on like the same line. How would it differentiate with that? Like, how would it
Yeah,
show it in the spectral?
so it's what's happening at that moment. So that's a good point. So let's take a lower image. So we're talking about systole. So in systole, we should be having the walls move together, correct? Okay. So if it's tracking the speckles and stuff inside here, and over time they're going from this image to this image, and we're still in systole. Let's look at our color bar real quick. The color red is coming towards the transducer, blue is away from the transducer. So this segment's going away. This part of that septum is at that moment actually going up. So when it squeezes, the top actually kind of kicks up a little bit where there's not as much muscle. So it kind of depends on what's going on. So at that exact moment, that's what's happening. You can see the right ventricular wall is going down. You can see the septal wall here is going down. This one by the aorta is kicking up just a bit. The posterior wall is coming up as it should. So this is actually a normal heart, the way it's working. And not all segments from base to apex are going to squeeze in at the exact same time either. So, you sort of get a motion like that, or the ringing of the rag kind of goes. If you had all of your muscle contracted exactly the same time, we would actually not have a very efficient ejection. But yeah, so that's going to give you some ideas. What we're going to pay attention to there is if there's timing issues. So if both of my walls on that segment, for example, were red at the same time, that would mean that my posterior wall is coming up and contracting, and my septum is actually going the wrong direction, but going upward. So that's how it would help us to tell what's going on at that moment.
So I was asking more specifically, we can't do color Doppler tissue or Doppler tissue imaging with color, and we can't do spectral at the same time, can we? Because it would just be too much noise between them. Or like we can only measure one specific part, right, with TDI. So that's where my confusion is like coming from.
So it's a good question. So the answer is yes, you can run them both at the same time, and often we do. But when we're running the spectral Doppler, and again, these two are not connected, but if I was to have a sample in here, your reference image at the top still has the color on there, but you're not really paying attention to that. You're paying attention to the spectral tracing at that moment. Presumably, you would have shown a good color Doppler of that if you had any concerns about that, just like we would show a color Doppler of a mitral regurgitation before we actually do the spectral through that. When we do the spectral, the color is still running on the top. We're just not paying attention to it as much. Does that answer your question? Or comment? Yes, sort of. Clear as mud. Okay.
Scott, I
So,
have a question. Sorry.
yeah, we're gonna-
Which machine in our class has this option?
for tissue Doppler,
Yeah, for tissue Doppler.
they all have it. Except, well, so obviously the ones that don't do echo don't have it. So like the Logic 9s don't do it. But all the echo systems do it except for the GEP5s. Those are the ones typically. I think there's one in room 7, maybe one in either room 5 or 6. So it's not that you can't do tissue Doppler, it's that you have to change a bunch of settings to make it optimal for that. Now it's on the board outside that room. So just as you walk into the back room there, that whiteboard that's there, I wrote out on the board what you need to do manually to make that a decent setting to be able to see that. And that's going to be involving moving your baseline, dropping your scale, taking your gain all the way down and your wall filter all the way down. And then you might need to also drop the power because these are very intense waveforms and it's very easy to over measure them because they're very intense. So you can take a look there. I walked by it this morning. I know it's still up there, but that's how you're going to optimize a system that doesn't have a setting for tissue Doppler. That's how you'll set it, and that's on PulseWave. And then it might be easier just to reset your preset than to go back in, because if you do that, when you go to do your next PulseWave Doppler, those settings are the same as what you just had. So you either need to set them all back to what they were or just reset the preset is the easier way. That help?
Yeah,
Yeah.
how do you reset the preset?
To reset the preset, just like you did at the beginning of the exam, you'll just go and on most systems, you'll have to go in and just reset it to the adult echo, what we call the global preset. Some systems like the Siemens products actually has sub presets that you can have an image control knob that leaves everything else the same, but will just change a few parameters, which they're really handy when you have. You can be doing like you could be doing this type of thing, and then you go in and have a setting just for tissue Doppler, and then you can change it back to the regular, flow Doppler, whatever it is, or you can have a setting for technically difficult patients versus an easy patient versus a super easy patient. So you can have different subsettings on some of these newer systems, which is quite handy. Some, especially the older systems, you have to just reset the entire preset, which puts it back to as if you put the probe down for the very first time in your parasternal long axis. So you might have to adjust your depth and your sector size and stuff like that. Okay, so tissue Doppler. So what was the advantage of tissue Doppler? What does it do for us?
It lets us see like wall motion abnormality or like a section not properly moving. And it better visualizes that instead of like 2D where we can kind of see it, gives us exact motion.
Yeah, so adding that Doppler perspective in the color map can help us visually see it better, because sometimes just watching it in 2D, you're just seeing a bunch of motion going on, and does your eye really perceive that difference of coming towards or away when it's supposed to, or compared to the other walls? So it can give us an indication there. Where we use it in spectral Doppler is typically on your septal or lateral walls to look for diastolic dysfunction, looking at our E and A wave and maybe even the S wave from that perspective. But technically, I could put tissue Doppler on anything from any perspective, and it kind of depends on what I'm looking for. The ones that we typically do are because it's been validated with a series of studies and different things that have proven that these are the results we expect to see in this situation. Does that mean that you can't use it for something else? No. If you get into a research lab, you might be using tissue Doppler for some other random thing, and maybe one day that becomes the new norm. So we are young enough in the industry that we may be exposed to some of that stuff and get to be a groundbreaker for whatever it is that we're doing. So what you want to do is keep in mind what tissue Doppler does specifically, and that tells us what it does is it tells us the general velocity and direction of the tissue itself. So that could be used in whatever way that you see fit, as long as your doctor's working with you and knows what you're talking about and what you're trying to accomplish. Throwing it out there just randomly and giving it to a doctor, they're not going to know what the heck to do with it. That's okay. So, okay, so tissue Doppler. And so the tissue Doppler was originally and still is kind of angle dependent. So the better angles you have, the better it is. I'm just going to jump back a slide here as we talked about color flow and color M mode. So don't forget that we have power Doppler imaging, stuff like that we've discussed in physics. They can be helpful to show flow in a slow flow state or flow that's not direction specific, but very, very sensitive. Okay. With this, if you go on to the Accuzon, I don't know if they've got it in the cardiac setting here, but on the room 1 Sequoia, they've got what's called Clarify Vascular Enhancement. So Clarify Vascular Enhancement is technically a 2D feature. It never actually goes fully into color Doppler, but it uses amplitude information that color Doppler or that power Doppler would have used. And what it does is it helps to eliminate the noise inside a vessel or something that that has flow in it. And that's done by velocity and just that sensitivity. It eliminates it from the picture so that you have a clearer picture of your vessel. Now, it doesn't just help with any fluid filled structures, it has to be moving fluid. So it has to be flow of some kind. Nancy, go ahead.
Do we ever use power Doppler? Because our velocities are fast.
Yeah, we really don't.
Okay.
Yeah, we really don't. It's used in general imaging because they get those very, very slow flow states. But it's important to be able to show flow, like in your kidney, for example. If we can't get that to light up with the color Doppler, you might need to use power Doppler to show what color flow can't really show you. My experience with new systems, though, is that color Doppler is so good nowadays that rarely would anybody really need to use power Doppler because our color Doppler is so sensitive. And if you do use power Doppler nowadays, the new versions of power Doppler can actually give you to and fro information, so we can see directional flow that was classically only given to us by color Doppler or spectral Doppler. So so now we've got these hybrid ones that are very, very sensitive slow flow states. But yes, in the cardiac world, we do deal with very, very fast flows. It's unlikely we're going to need that. But it could still be on a registry, so you never know. All right, so let's get into, so these are the slides that I added about 3D. And this, again, just as giving us a synopsis of 3D, we could spend almost a whole quarter just doing 3D alone. There's that much information if we really get into it. So I just want to give you an idea of what 3D 4D is and kind of how to manipulate it, at least to a mild degree. Once you get good at it and you start using a lab that has it, you'll get pretty quick at it. But it's almost like learning 2D all over again. So with 3D 4D, it's a XYZ axis. So again, our XY, we're familiar with that on our two-dimensional image, okay? And then the Z axis, we always draw it in a line because we're trying to portray it on the 2D image, but it's this axis is coming in and out of the screen towards and away from you. And so our three-dimensional image is made up of a 2D image with stacks of additional images that kind of make up a volume of information. So when we talk about a pixel on the screen, we're talking about a two-dimensional representation of a spot that we're looking at. Pixels aren't exactly dots. They have their own characteristics to them, but it's on a 2D display. A three-dimensional display, that same piece of information has also got a three-dimensional depth to it, and we call that a voxel instead of a pixel. Because when you're talking in 3D, it's called a voxel. And when we're talking about frame rates, that's a two-dimensional term. When we're talking about rates in 3D, we're talking about volume rates, which means that you have to have, like 250, for example, 250 slices at that high frame rate to be able to produce that whole thing. So not only do we have to go line to line as we create our image for 2D, Now I got to go in a volumetric way in that elevational plane. I have to add additional frames that take that much more time to create. So 3D 4D volume rates get very, very slow. Okay, so it's very difficult to get a good volume with good resolution in real time. Okay, so very, very few systems can even do a real time decent sized sector. So just to give a quick rundown, so we're going to be talking about the X, Y, Z axis, and I put these little rotational things here. So when we have an ultrasound system and we take a 3D 4D image, I'm going to show you some images here just in how you look at it. But I want to take that single image and we need to manipulate it. So I need to turn it and twist it and tilt it different ways to be able to represent what we need. And we're going to do that by changing the X, Y, and Z axes. On your ultrasound system, so if you go into room 1 on the Sequoia, you'll see, I can't remember which keys it's around, but there will be 3 keys that are labeled with an X, Y, Z beside the key. So when I'm in 3D mode, those keys or those rotary control knobs will control those X, Y, and Z axes. So when I turn the X axis, for example, the system is going to turn your image. So I've made a cool little representation here. So here's a little printout. So there's our picture. Okay, so this is my X axis. This is my Y axis. That's my Z axis. Okay, so what I want to know is this picture, when I turn the X axis, it's going to turn my image like this. Okay, when I turn the
I'm
Y
sorry,
axis,
can you make it a focus or is that just me?
it's probably horribly focused. Is that better?
Like the focus, like your screen sharing is the main camera. Is that just me? How can I fix that? Anyone?
Yeah, so you're not the main window we're seeing is your
Oh.
PowerPoint and not you.
Gotcha.
If you're on a computer, you can just take and drag the middle, but I think, Nancy, you're probably on an iPad, right?
But let me fix it for you.
I'm on
Hold
a
on.
laptop and he's small.
I got you.
Yeah, you can just take and drag the middle. There should be a cursor bar in between his shared screen and him. That on mine there is at least.
I'll
That's a helpful tip.
Zoom.
Yes, thank you, Larissa. That works.
You're welcome.
Are you good?
Yep.
Okay, sorry about that. I was just about to say that, but we'll stay here. So let me jump back to this. Okay, so here's my picture. You'll see that. So again, X-axis, Y-axis, Z-axis is going in and out. So if I turn my Y-axis and when we rotate that, you want to see what happens to your picture. So when I turn on the X-axis, it's going to rotate this way. Okay. When I take my Y-axis and I rotate it, it's going to rotate that way. If I take my Z-axis and rotate it, it's going to just turn the image on the screen. Okay. So again, that's just a very down and dirty. You really have to get used to this by practicing with a real 3D sample and being able to manipulate it around. So that's how we turn the axis, and that's how it's going to change it as I scroll. These next images here are just kind of explaining what to see on a 3D image. So this is a uterus. Doesn't matter. I just found these online. But the way it typically represents is a couple different ways, and I'll show you a couple different ways here. So in the 3D world, so you're going to have your reference image. So this image A, so we have image A, B, C, and then you have your 3D rendered image on the screen. Okay. This is your normal scanning plane. So whatever indicator side you have in that orientation, this is the image you normally see on your screen. Image B is 90 degrees to that. Okay, so it's A there, 90 degrees to that represents image B. Okay, and then if you look from the top down, this is what we call the en face view. This is image C, so that's looking down straight on top of the uterus. So this is the uterus right here, okay, in a long axis. This is 90 degrees to that. This is a short axis of that, 90 degrees to that first one. And then 90 degrees, but looking straight down at it is this C image, which kind of shows where the endometrium goes out side to side. The rendered image happens to be linked to image C and turned upright this way. So the uterus is placed with the fundus up, cervix down at the bottom. You got right and left sides there, and you're looking down from on top. Now I can control that different ways. Okay, so first of all is knowing that these three images here are 90 degrees to each other on a normal 3D rendering. This line that's in here that I'm pointing to, it's kind of a little box. Okay, this box is telling me how much information I'm going to display in that rendering. Because if I just took the whole rendering and showed that as a whole, I would see like a volcano. I would see like a mountain, and that's all you're going to see is the outside of that whole sector. So we narrow it down by focusing down and thinning that that area of reference around it. The green line on that is the line that we're looking at it from. So my eyeball is looking down this way towards that volume when it's displayed like this. Okay, so that just tells you how I'm looking at it. And again, just knowing that these are 390-degree or orthogonal planes to image A. So that's one way to display it. Back to this real quick. So this is my normal image. So my video is really slow. You guys hearing me okay?
Yeah.
I just want to make sure that I'm keeping up with what I'm seeing, because what I'm seeing on my screen is different. So this is your normal image. These are what we call rendered images. All of the rest of these three are actually rendered images, meaning that it's taking the data that it got from all those slices, and it is the computer is creating that image based off of those. So this is the only true image that we see like we normally see it. Unless you have a matrix transducer which can show both of these in the same way, image C will always be a rendered image, and then the 3D, the volume slice is also a rendered image, meaning that the computer processed it based off the other slices. Okay, here's a cardiac one. This is off the SC2000. So this is a sister system to the S2000 we have in, or the Sequoia that we have in room 1, or its predecessor. So this case, we have image A, B, and C labeled this way. This is one of my favorite 3D systems ever. It had just such a great 3D software package. What the last one didn't show is that you now have references to what I'm looking at. So notice around each frame, this might be faint, but you can see a red box around box A. You can see a green box around box B, and you can see this blue box around image C. So when I'm in reference A or B, I can see that so I see what's happening in image A, but what if I want to know how it's interacting with image slice B and C? B is represented with this green line here, that represents this box. And then this blue line is what image C is seeing. So you can see how it's interfacing with that. So if I was to look at that and wonder if I'm in the middle of my ventricle, for example, I can tell that I'm not in the middle of the ventricle. In fact, the apex is over here. So if I wanted to see that, I would have to line image A up so that my green line goes right through the middle of the ventricle. So this image is not the most open. This is a foreshortened view of the that ventricle. This image note is linked to image A. So the last image here, this image was linked to C. In this case, it's linked to A because it looks the same. This is a 4-chamber view. And then anyway, you can correspond what's happening to that. So if I'm in image C, for example, I can see that the red line corresponds to what I'm looking at in this image up here in image A. So I like this system because these color-coded boxes tell me what's going on in the other views. Again, it gets to be fairly complicated, so I'm not going to go too much into that detail. What other feature they have on here is I'm pointing, you can't see this maybe super well, but this arrow here is pointing to a little line right there on top of this line. And that's saying that when I'm looking at image C, which represents this blue line, that arrow is pointing down from where my eyeball is looking at it. So I'm looking at this image C from the apex towards the atria. So I'm looking down at the valve. from the ventricle. Or in anatomical cases, I'm actually looking up towards the valve. But this tells me what direction the lines are, or what perspective we're looking at that line from. So if I'm looking at image B on the green one, I'm actually looking at this image here from the lateral towards the septal. So if I could see into this of any detail, I'm looking, let's see, yeah, image B is looking towards the septum, for example. So if this is linked to A, okay, and I'm looking into the back of A, I might go to image B here. Box A is represented by this red line here. I'm actually looking up towards like the aorta. So I'm looking anteriorly from posterior, or from inferior to anterior, or from posterior to anterior. So I'm looking up in here towards where the aorta would be.
Scott, does this just click out in the freaking clinical field? Because you're losing me.
Dude, that's why we're just touching on it, because like I say, when we're doing this with, when we're training techs to do this, you could literally take a whole quarter spending on just how to manipulate 3D images, because it's not that easy. We find that techs often find it as difficult to learn 3D as it did to learn 2D the first time.
I'm feeling that right now. I'm like, I can't even like follow.
Yeah, and you know, some people might get it faster, like people that are gamers, for example, they're used to that whole 3D world and manipulation and stuff like that. People like that that are used to that might grab onto this faster. I'd say the average tech does struggle with this. So don't feel bad about that. It is kind of natural. It will take some time to figure out, and it's hands-on. You know, when you get an image in your hands and you get to control that X, Y, and Z axis, you know. And then you get to the point of doing those manipulations, you know, turning on my y-axis or my x-axis or the z-axis. You'll get used to that, but then you need to take your anatomy inside there and line it up so that it's perfectly, you know, if I'm going for a non-foreshortened left ventricle, I need to get it right at the apex. It can't be cutting off any of the apex. So now I've got to take and manipulate it so I can see that exactly by using those 3 images to do it. So it does take a skill to do. Once you get there, you'll get some tips and tricks that you can do it much faster. I was able to take, because I would demo this stuff with Siemens. We have what's called stick imaging. It's spatiotemporal image correlation, and it's a 3D rendering of a real time of a fetal heart. So in the fetus inside the mother. I can take a volume of that, and I can take that and I can get all of the required 2D views out of that one 3D image by manipulating it. And once you get good at it, I was able to manipulate and get all those images in about 1.5 minutes if you have a good volume. But it does take a lot of practice to get it down quite good. Some people will take onto it faster than others. That happens, but most of us are going to struggle with it.
It sounds like kind of some of the VR tech that they have nowadays with the
Oh,
goggles
totally.
and stuff. So
Yeah, I think 3D
I
is
could see
super
cool
cool.
parallels to that.
So 3D. So if you remember back to transducers, our wobbler transducers are the mechanical transducers. So they have a beam, a set of crystals that's physically moved from side to side and sweeps back and forth to create these images. The other way to do it is a matrix transducer that doesn't wobble. It has a full square of crystals that can shoot in different planes. That's how a lot of the TEEs are done. So in the echo world, most 3D is still done with transesophageal echo and not 2D transthoracic echo. Transthoracic echo takes a bigger transducer, and we're already struggling between rib spaces and stuff like that, so it's difficult. But there are systems that do it. This SC2000 that you're seeing here, this actually uses a matrix transducer, and it's a flash technology. So instead of reading line to line, it actually flashes all the lines at one time, and then it has a brief cooling period that's really imperceptible to you. But from an imaging and computer standpoint, it has to go very fast, and it's actually a liquid-cooled transducer because one of the biggest issues is heating. So it's very complex the way that it's set up to do it. once you get good at doing it, it's really not that bad, but it will take some time to get used to. But don't feel bad about not just grabbing on right away and going with it. Nancy, go ahead.
That you said heating, is that the body or the probe?
That's the probe.
Okay.
Yep, so the crystals actually do get warm. Even when you're scanning, you can hear, if you ever had the harmonics on and had the transducer sitting on the system, you hear kind of this chirping sound. You might notice that when you're in the lab, particularly when harmonics is on, but you'll hear that chirping sound, and that's interaction with the crystals. That's what's happening. It's ringing. When you ring those crystals, we do create heat within the crystals, and one of the biggest problems with 3D matrix transducers is their heating problems. That's part of the reason they can't do some of the manipulation they do, is because by FDA clearance, we're not allowed to get so much heating. So with Siemens, they flash it, which gets all of our stuff at the same time. It's a ton of processing, but the crystals need a moment to cool. And they still had issues, which is why they made a liquid cooled transducer. So there's actually liquid runs right into the transducer and back to the system through a fan system, just like your car has a cooling system. Those transducers had cooling systems, which is kind of cool, which adds to the bulkiness of the transducer. So you have all these physics considerations when somebody's building an ultrasound system. You can't just take this cool idea of, hey, I want a matrix transducer that scans in real time in volumes and is cordless. You know, those are things that are physically difficult to overcome totally. So that's what physicists do in the ultrasound world, is they find different ways to overcome these issues that we have. What was also cool about this system, because if I wanted to do, for example, I want to show a good 4D view, and I want to show a good 2D view with the correct walls at the same time. Do you think that's possible the way that we're set up here? What do you know about the 2D compared to the 4D or 4-chamber view and 2-chamber view in the apical long axis or apical view? Are they lined up with each other if I was at 90 degrees? So how much of a turn do you need to go from your 4-chamber to your 2-chamber to your 3-chamber?
60?
60 degrees. So are they lined up at 90? No. So if I did this orthogonal view, I couldn't really show a true 4-chamber and a 2-chamber at the exact same time. I would not be representing the correct walls. So on this particular system, and others may do the same, is it gave the ability to unlock that 90-degree angle so I can make it more 60 degrees. So I could actually unlock those planes so that they didn't stay at 90 degrees. And therefore I could show my true apical long, or my, well, I could show apical long axis, apical 2-chamber, and apical 4-chamber all at the same time, which is pretty dang cool. So those are the tools inside the 3D system of that particular vendor. Each vendor does theirs a little bit differently, but those tools make your manipulation of the images much, much easier if you know what you're doing. And then, so again, that was the rendered image here. Okay, this is our A, B, and C, just represented vertically on top of each other. It's just important to know which one is which. So do that not switch on me? There it is. Okay, this is another one. This is called MPR. This is multiplanar reconstruction. So in where we see MPR and where they got the idea of MPR from is actually from nuclear medicine. So whoever's doing their project on nuke med, you'll see that they have all these different slices through the object that you're interested in. So in this case with ultrasound, we took that same concept because it can be helpful to us. So we've got our same A, B, and C labeled here. Okay, so this is A, is always on the top left. In this case, B is beside it, and C is beside it again. Actually, these look to be the same images, actually. So they've changed the perspective on this, but we've got these images beside it. On image B in particular, you can see additional vertical lines through this, okay? Each of these vertical lines is represented by one slice. So this is showing that each individual slice represented down here from top to bottom, left to right. Okay, So as I'm progressing through it, for example, I'm getting this image off this slice, this last image will be this last slice. And I'm seeing all the way through that object. Now
Are
they're
you
doing-
looking this way or this way?
I believe it's looking from left to right, but I can't tell 100%. But typically on the heart, we would have these beating. So you would actually see these beating various places. In this case, what they're interested in likely is the valve itself. So they're looking at the actual valve, not as much probably the chamber, but they want to see what's happening as they progressively go through that image.
And that's A1, A2, A3?
Basically, yeah. And so you can display that as a whole multiplanar display. So all you see is the little images across the screen. You don't see the other 3 reference images. You can change your display format to see what you want to see. And even when you're doing 3D, you can blow it up so you only see the 3D rendering. You don't have to see those other slices. And then this last one, I've just got a bunch of clips. These are just GIF images from online of different representations of 3D cardiac stuff. Okay, so looks like my laser pointer is not going to be. Sorry, this is taking a lot of processing, so my laser pointer is not working super well. But the top image there is transesophageal. It is you're seeing the mitral regurgitation. Now that wire frame thing that's in there, that's a measurement that's happening. So there's a whole pile of measurements going on that are overlaid onto that 3D image. Same thing with the aortic valve is to the upper left of that upper left image. You can see there's a little bit of aortic insufficiency coming back as well out of that. Okay, and then it kind of
And
shows where the valve.
regurg, right?
Yeah, so aortic regurgitation and mitral regurgitation both. So that's kind of cool. The next image over on the top middle is aortic valve, I believe. It's a valve regardless. That might be mitral valve actually. So you're seeing the valve leaflet, and we're not just seeing a slice of it now, we're actually seeing part of the leaflet itself. You're seeing the back wall. I mentioned before that in 3D, they started using what they call depth maps. So you can see a different perception as it's deeper into a structure. So those more purpley bluish hues are deeper in the structure than otherwise. Because initially in 3D, all you saw was it was all yellow or whatever color they made it. And it was difficult to perceive what was going on. Top right, so that is a multiplanar reconstruction, the MPR that I just showed you. So you've got your 3 reference images on the left, but then you've got it consecutively through the LV from the apex down to the base. It looks like it's gone down to mid, where the papillary muscles are. So that can be very helpful again to see wall motion segments more specifically throughout the heart. Then you have a mitral valve down on the middle left. The the funky thing there, the green wiry frame thing is basically eliminating all the heart, but showing you the calculated chamber measurements. So it's showing you the internal chamber beating, and that's the internal volume. Where that's been super helpful is being able to get a really good right heart information because the right heart has such an odd shape. So you might see that. So we've actually totally eliminated all the echo of the heart, and you're only seeing the rendered calculation of the volume that's beating. That's kind of cool. The middle level to the right is, I believe it's a balloon of a mitral valve. So you're seeing that balloon inflate. It's deflated right now. There's it inflated. So they can use 3D to watch procedures and make.
Can
sure
you
that
touch when it's deflated and inflated?
So right now it's deflated. My laser's not working. And okay, hold on. Deflated now. Now it's inflated. So you see in the center of it, it just expands.
So when that like half moon kind of comes in on that left portion of it, that's inflated.
That's deflated when you see the half moon.
Oh, okay.
And the structure was like the belly button pokey in the middle of the full inflated one? Is that like the end of a balloon?
So that's the catheter coming in.
Oh, that's the catheter.
Yep. So we're seeing the catheter cross-sectional, and then you're seeing the balloon kind of surface rendering of it.
Why
So
do you do
where,
that? Oh, sorry. Go ahead.
well, I'm just trying to figure out where's the TEE camera here?
Oh, so this is likely up in the left atria, or behind the left atria. So it's in the esophagus, but it's imaging from the atria towards the ventricle.
Okay. I guess
And
I can
so
picture that.
so the heart catheter is, I believe, actually poking through the interatrial septum, coming across, and then it bends down and goes directly down into the mitral valve.
So that's not, okay, so we're not talking about ICE, we're talking about TEE still, right?
Yeah, this is an interventional procedure here. We're doing TEE with an interventional procedure. Yeah,
ICE
could be-
cannot perform 3D?
They could, but then you're taking up that same space in the catheter with your ICE transducer. So it just takes up more space. And could they do that? Yeah, sure, they could do it. It just depends on how much space they have to work with. All right, the lower left image there is it's kind of tissue Doppler in 3D. So you see a rendering of the ventricle itself overlaid onto a single slice, and it's kind of going through it. Where that green plane is going through is actually showing you what's happening at that level. Well, that's your bullet view that you'd see like on a or the bullseye perspective, that you can see the apical sections, you can see the mid, you can see the base all at the same time. That of that lower left image, the lower right part of that image. So it shows the reds and the blues. So they're seeing where the wall motion abnormalities are occurring at from a tissue Doppler perspective. The lower middle one is of a great big, I didn't get what the image was. It's either a mass or it's like a thrombus or something that's coming in and out of the left atria through the mitral valve. So
That looks gigantic.
plopping back and forth. And so when we get masses called myxomas, we often see that. They do get very large and they come in and out of the valve. It's scary looking. The
So
last one, the lower right, is a valve replacement. It's a bileaflet valve. So you can see the two leaflets of the valve itself. You see a whole bunch of dots around that valve. That's where they've sewn it on. Okay, those are little sutures. So you can see the valve opening and closing. You can see the little double leaflet. So they're little hard plastic type tips that kind of rock back and forth. And around the outside of that valve, you see a little hole below that. That's showing what they call a dehiscence, or where the valve is coming away from, the valve annulus has come away from the edge. And we would end up getting a leak through that area. So those are just some examples of 3D, 4D. What is the difference between 3D and 4D?
Real time.
Yes, so 3D is three-dimensional. 4D, the 4D, the fourth dimension, is time. Kelsey, go ahead.
That middle bottom picture, that's not with TEE, correct? That's with like one of those matrix probes?
Yeah, this would be a matrix probe, transthoracic. So just our normal echo position, but with a 3D transducer. Pretty cool, huh? So the kicker is, how do I get this volume of information and display it correctly? You know, it's hard enough to get our 2D slices angled correctly. So 3D is now taking it and finding it and aligning it in such a way that I see the way that we're supposed to see it. That's the trick with 3D 4D. Now, most of the images that are done with 3D are actually stitched together with 5 beats of information consecutively, and it will take a thin slice over one side, and then it progressively goes across to the other side to create a full 3D rendered image that you can see. And then they run it, and it looks like it's real time, but it's actually 5 consecutive beats that are making that up. And where they put those together, they can sometimes come up with artifacts because it doesn't always align if you don't have a perfectly regular rhythm. and they get what's called stitching artifacts where things don't quite line up the way that you think that they would. And that's because of splicing 5 beats together to make up your picture. Did you have a question, Nancy?
Yeah. So out of these 9 images, if you were to ask me which one is 3D and which one is 4D, how do I know that?
If it's moving, it's likely technically 4D is what they would call it. I'm not gonna ask you that question. I just put it out there because I'm always like, well, what? I know what 3D is. What's 4D?
That's how I feel. So I'm like, I don't know what that means.
So yeah, 4th dimension just means that it's moving. In reality, most echoes don't really, to be considered real time in 2D, we have to have 25 frames per second. To be considered real time in 4D, you'd have to have 25 volumes per second, which is unheard of. So most of what you see in 3D that's moving is not actually real time.
It's like a stop animation is what you said.
Yeah, so these are you can see that they're very choppy already, right? So they're not really going in real time, most of these. There are systems now that can do it though, but it takes an immense amount of computer processing. All right, so I just want to give you an idea of 3D, 4D. So it's very basic. What I'm after is just, what's the concept of it? How's it different from 2D? Just note that for good 3D images, you have to have not only a good single slice that we get for our 2D, but you have to have a whole volume of those slices in an elevational plane without artifacts to be able to get a good 3D image. So while everybody thought that 3D 4D was going to take over and make our techs lose their jobs because now we don't need techs to do this anymore, the reality is the tech still needs to find good images and good windows. So 3D 4D has been around for probably 25 years now. Clinically, it's been useful regularly in the cardiac world for probably a good 15 years, but we're still not totally there yet as far as where we want to be, because it does take a lot of manipulation from a person to find the good slices and everything that they need to. So it's not super easy, but when you can get good information, it is good. And the 2D quality of a single slice is still better than the quality of a slice of 3D information is also. So it tends to be very smoothed out. Doesn't have the greatest 2D resolution, although those things are getting better. Okay, so acquisition of cardiac ultrasound information, just other things that the chapter had brought up. So transthoracic echocardiography is what we do, scanning across the chest. Hand-carried ultrasound systems. So I just made notes on, in the industry now, not only do you have your full-size ultrasound system, we have laptops, we have cordless transducers in small systems that go into the cath labs. We've got dedicated single-line interrogation transducers, transesophageal, 3-dimensional, epicardial imaging, meaning that you can take your transducer and actually scan on top of the heart during open heart surgery. ICE, so intracardiac ultrasound, and IVUS, which is intravascular ultrasound. Beyond this, you have handheld ones now. So we've had handheld ones for quite a while that are about the size of a cell phone. They're hooked to a cord and a transducer. Now you can literally get a cell phone, a smartphone, or an iPad or something like that. You can plug in a transducer into it, and now they've even got them that are cordless that just wirelessly connect to your or Bluetooth to your cell phone, and you can scan off those. Yeah, go ahead, Nancy.
Is that the hand carried ultrasound? Does that fall under that one?
It would, yes. Yeah, so they're coming of all types and sizes. Now, Butterfly is one example of that. Multiple vendors now have these, and some of them you can buy one time and you have. You're buying a transducer essentially, and then you're getting an app for your phone. The Butterfly one is actually a cordless transducer, so it connects to it. And I did find out from the manufacturer that they don't use piezoelectric crystals. Remember I told you about the lithographic process of printing them? That's what they're using currently. So it is clinically being used. These transducers are about $2,000 that you buy them for now. And so now the local medical school actually requires that all their medical students buy one of these. And then they have a subscription that they pay each year for the service to be able to run the software.
I considered getting one.
Yeah, I would love to have one. So the new Butterfly, apparently you have kind of a curvilinear type of transducer that because it's those lithographic printed transducers without piezoelectric crystals, they can do a phased array transducer, they can do linear transducer, they can do curve transducer, all based off that same one. They just fire the elements differently. And that's how they accomplish what they need to. And does it do everything that our high-end system does? No, it's not going to have quite the capabilities. But the fact that it's even here and is being used is awesome, because 10 years ago, people would have told you you're crazy. It's never going to be like that. So I think it's pretty cool. So now that they've got those types of crystals, or not having crystals, but those types of printed elements, we can make all kinds of different shapes of transducers with tons and tons of redundancy on its capabilities. We can start using annular array type of setups now. We can start doing things that have been gone for a long time because crystals weren't very good at them. But now it opens the door to other things. So future of ultrasound, just know that all these types of things are out there. Know that the quality of the handheld ones are not going to be the same as the high-end system. There's just so much more processing goes into play. All right, and then the rest of this is speckle tracking that we've already gone over. So it's basically the idea of taking and identifying individual bits of speckle and tracking them from frame to frame, seeing where the motion takes us, and then extrapolating graphs and data and stuff from those. So I'm going to go to the end of this. So you've had this before, just as a very basic explanation of it. And that was that velocity vector imaging that Siemens had. Acroson. I think I had some stuff at the very end. I might not have. Okay, no, that is in fact the end. And then just goes over the digital echo lab in the end, just showing that you've got your servers and your PAC systems, your different departments and stuff like that. And that was just mentioned in that as well. So you've got your OR, you've got your stress testing, you've got remote nodes. Typically, all this stuff had to be connected with an Ethernet cable. Now, like our room 1 and 2, for example, those systems actually will send wirelessly. So the wireless stuff is a reality now in the hospitals. So you don't have to plug into a wall somewhere and send your images. They can send on the fly as you're doing your case. So, as technology gets better and better, we expect more and more of that to get integrated into the hospitals and clinics that we work in, and make our job just that much easier. You can do teleradiology with stuff like this, so you could actually be scanning remotely out in Republic, Washington, for example, and getting your images down in Spokane or even a Duke Medical Center in North Carolina or something. So that is specialized techniques. That's the other stuff that kind of goes on with Echo. Any questions about that?
I do have a question when we're talking about the study guide. It asks, how does speckle tracing or tracking relate to contraction timing?
Yes. So let me jump to, let's take, this. Let me throw this over here. Can you see that?
It does it by vectors.
Yeah, so this one's vectors. They're not all vectors per se, but what's happening is I can take a point over here and a point over here. So septal wall compared to lateral wall. And on graph, it's kind of graphed out here, but where these happen to be squeezing in at the same time. But if it was off the timing, I would see like the peak of one, for example. We'll go to the circle one up here. I could take the peak of one and maybe another peak is delayed and is peaking over here. So those graphs can show me graphically that they're not squeezing at the same time. When one's coming in, the other's going out. Okay, so the squeeze is going like this instead of like this. Okay, so I can take dots of the information, one single arrow from here and take a single arrow from another spot and compare them.
Oh, okay. So it's just basically asking how that information would look on a graph if they were off contracting from each other.
Right, and so here's another image, just a bunch of graphs and stuff here. You can see there's a complex set of stuff going on. They can even display it in, there's the bottom of the image, you can see this M mode with the reds and blues. So here's one that's normal on top, and the one that's below that is abnormal. So you can see that they should be lining up red, blue, but across this one, you've got, it's kind of all over the place. And that can show you that the timing is off. And
So-
or it's not squeezing at all.
Would you expect us to be able to read and understand those graphs?
No,
Okay, thank you.
no. So there's as much information in one picture that we're seeing here as there is in all of the 3D we just discussed. I mean, there's a ton of information. I do not expect you to be fluent at that at this point.
Yes, it's a ton of information, and that gal from Siemens went over some of that with us. It's pretty interesting, but it's a lot.
It's super cool, but you can get as much information in one clip as you do an entire study. If you know what I'm talking about.
She was really great. She showed us a lot of things.
Yeah, it's cool. That's what I found fun about working for the vendors is you have access to that, but you also have access to the engineers that make it, and you get to talk to some of them, and it's just really cool. Kelsey.
Yeah, so touching on Angela from Siemens, she was saying how if for the Siemens system, anything under -20, meaning closer to 0, means that there is desynchrony. Is that system wide?
It might depend on the vendor. It just depends on how they do their measurement. If they do it the same way, it would be the same. But like strain imaging in general ultrasound, for example, Siemens uses shear waves, which so when a wave comes out from the transducer, there's waves that go off laterally. Those are called shear waves. Typically, those have been ignored, but now they've started to use those and measure how fast those are to determine how stiff the tissue is, like in the liver. So Siemens does it by velocity. GE does it by, and I can't remember how GE does it. They do it by a different mechanism, different type of measurement. So it just depends on what they use for their measurement and how it's validated. So sometimes they can be the same, sometimes they're not. Yeah, Nancy?
So strain really just helps us identify and quantify abnormality and dysynchronization, right?
It's a small part of it. It can, but it can do a lot of other things too. So strain fundamentally just means how much pressure does it take to deform those pixels or that tissue. That's really what we're talking about, is how much pressure does it take to deform those tissues compared to tissues around it. And strain rate is how fast does it deform. And then there's a whole pile of information that we can derive from that information. So including timing, including just, the stiffness of the muscle itself as far as, hypertrophy goes versus a wall that's scarred, those types of things. So the strain fundamentally is just how much pressure does it take to deform. Strain rate is how fast does that deform compared to tissues around it. And again, tons and tons of information we can get from it. Yeah.
And deform is a good thing unless it's not too much, right? Deform is, we need it to deform.
Yeah, so what we mean is like if I was to palpate the bone in my arm, when you push, from a doctor standpoint, if they're pushing in on the outside of your body, they can feel that it's hard right there. If I go over here, it's soft. Okay, so this strain imaging is basically, instead of us poking at somebody, we're actually kind of poking at them digitally with electronics, with the sound beam. And that sound beam is giving us those characteristics of stiffness. And the stiffness could be good or could be bad. We want things to be relatively stiff. If you get a lot of fatty infiltration, for example, it might get softer. If you get something where there's a lot of collagen and fibers and stuff like that, it becomes stiffer. So it depends on the pathological situation. Strain and strain rates always compared to what's going on around it at that time. So it could be a good thing, it could be a bad thing, depending on what you're talking about.
I have another question.
Yeah, go ahead.
It's following the rabbit hole of my brain. This relates to bulk modulus.
Vaguely, yes. Not as direct of a correlation as you'd think. It's bulk modulus is more the tissue characteristics of stiffness and how it interacts with ultrasound. This strain imaging is just simply looking at the deformation of these pixels relative to the tissues around it. So if I'm comparing the septal wall, for example, I'm comparing it to a posterior wall or a different wall. Now, some things you can track over time. For liver strain imaging, for example, they actually do track them over time with that same patient, but they may not follow the exact textbook to other patients per se. But we're trying to see if it's getting better or getting worse as a trend generally. It's not going to say you definitely have this disease because you have this stiffness. It's kind of a correlation.
Yeah, I was watching him kind of do a little bit of that on Rachel's liver because, you know, obviously she's got some disease processes going on, but it looks like they don't really have a specific spot they take it. They just kind of just like sample different areas.
Yes, and so just like us measuring a whole bunch of waveforms consecutively, it's the same concept. It may not be the same wave and everything, but the more measurements that you put into the data collection, the better your average results are. And that's essentially what we're doing. They're sampling different spots to see if it's similar. Now you usually have to have some parameters. It has to be like within 2 to 3 centimeters. It has to be in a certain area. They probably can't have vessels and stuff in where they do the sample, stuff like that. So there will be some parameters that they follow. And for what they're doing is a specific disease pathology that they're looking at. They may do it also to look at a tumor versus normal tissue. They could use it for, there's innumerable things that they could use it for. That's just one application of it. Like I said, there's so much information in this strain imaging, both with cardiac and with general imaging, that we're only scratching the surface of what it can tell us. And that's just in one clip. So specialized techniques, just in the end, the take-home message is there's lots of cool stuff out there. It's beyond just 2D and Doppler imaging. It's there's all kinds of things that they're studying. My message is always be open-minded. When vendors come in with a different technology, check it out. Sometimes it's going to be useful. Sometimes it's not going to be useful. Sometimes you think it's useful, and then you take it to your doctor, and your doctor's like, whatever, and they don't use it. So don't be offended by that. It is what it is. 3D's been around forever, and there's still a lot of clinics that don't ever use 3D. Will they at some point? Maybe they won't. There's a lot of people that like to wait for something to become validated and widely used before they ever implement it, so that they don't have to have those growing pains of starting new technology. So my advice is to my students is embrace new technologies, check it out. Artificial intelligence is part of all of this. Artificial intelligence is being used to diagnose disease that we don't even visually pick up with our eyeballs. And I think it's super cool. So could we use it to benefit mankind? Yes. Could it be scary in some ways? Yes, but it's fun. So embrace the new technology, be the innovators of the future. If we sit back and resist it, we get left behind. With that,
I have one more question on the study guide. It asks, why is Doppler-based speckle tracking suboptimal?
so just Doppler generally, what is the weakness of Doppler?
Angle dependent.
Yes. So if we use Doppler-based speckle tracking, angle dependency is the biggest issue. So speckle tracking speckle tracking, identifying speckle and its movement is much more accurate because it's all 2D based, it's not Doppler based. So that velocity vector imaging, for example, it doesn't matter what angle it is, it's tracking the speckle movement and not the Doppler shift. Make sense? All right. On that note, go enjoy some sunshine.
Scott,
Yeah,
can you post the updated PowerPoint for us?
yep, I'll do that right now.
So we
Yay,
have
thank you.
tomorrow before class and then class following, correct?
Say that again.
We have a test tomorrow morning before class and then class following.
Yes.
Okay.
Yep. So specialized techniques, take the quiz. Yep. Good, good. See you later.
Thank you.